So that seems really easy, and it is really easy. Let me just run that again and put some things on top. So it's under Tools, Basic Fitting, Linear and Quadratic. There we go. And we can get the formulas. What I'm going to do now is critique the whole entire enterprise that we are embarked on now. There are some assumptions built into what is happening here. I need to break those down a little bit, and then we can talk about when those systems are going to lead us astray or when they're totally fine. So when we talk about this line, somehow, out of all the possible straight lines in the world, this is the one that MATLAB said is the best. So we have to define ourselves, or define what best means here. We have choices here. We have the best straight line in the whole wide world. That's the yellow line. And we have the best quadratic line in the whole wide world, that purple line. They're both the best in some sense. How are we supposed to pick between them? Especially if we ask, well, not just quadratics and linear, but we can actually add cubics, fourth order, fifth degree, sixth degree, seventh degree. Starts yelling at us after a while. But there are lots of best curves here. Let's go back to the first three, say, up to cubic. Which of these is, in your mind, the most appropriate? Which describes the data the best, in whatever way you want to think of best here? Yeah? The residuals. OK, we can talk about that in a second. Just in terms of which, so you'd say the cubic then, because it has the lowest residual? OK. The quadratic, because it just seems nicer. Right. Here we have there's two issues. One is numeric quality. So let me go back. So let me ask, could someone define a residual for me then, if we all know what it is? Yeah. Distance from the point, the actual data point, to the best fit line. Absolutely. There might be a square and some square roots and stuff going on in there, but absolutely. If I go from the linear to the quadratic to the cubic, what's going to happen to the residuals as I go that way, as I add more degrees to my fit? Are the residuals going to go down then up, or always down? This is the essence of the problem right here. So if I have a fourth degree polynomial, I have lots of choice. And in fact, all of my choices, could one of my choices be a cubic? Yeah, fourth degrees are cubics with a fourth degree added on the end. So no matter what, if I go to the next degree down, I have more flexibility, and I could also get the same graph I got last time. And the way these graphs are built is it tries to minimize the residual. So at worst, your residual will be the same, but in almost every case, at least be a little bit lower, because you have a little more flexibility. You can tweak your line a little to just get closer to one more data point, and your residual will go down. So I'm just going to show that quickly here. If we look at our linear, residual is 209. Quadratic, 190. Cubic, 186, going down. 185. 184. And then, start getting longer, 184.9. These are going, they have to, mathematically, as you use higher and higher degrees, you have to have lower residuals. Because otherwise the math doesn't work out right. You have more choices, you can get closer to your data. There's no other way. It certainly can't be any worse. What that means is residuals are completely useless at deciding between which curve is the best one. Because by residuals, the 25th degree polynomial will be the best one, because it'll have the lowest residual. So whatever you get in your mind, residuals don't let you pick between best line and best quadratic. They can't. Okay? And this is where we actually get some of the same flavor of interpolation. There is no single best choice here. There is the best single line, but if I'm choosing between lines and quadratics, you get to that other statement or approach, which is, well, I think the quadratic fits better because it just fits better. It looks better. And honest to God, there are almost religious wars about what kind of fit should be used in certain contexts, because there is no single answer that makes sense. If you don't have any a priori reason to say quizzes and exam marks are related by quadratic functions, and we don't, they're just marks, then someone could say, I think the linear is a more appropriate fit because there should be some sort of simple relationship. Someone else says that, well, no, there's a bend to the data. I can see there's a trend, and so it should be quadratic. And then the cubic person comes along and says, well, down near the bottom end, maybe it's a better. There is no single right answer. I just wanted to hammer that home. There is no single right answer, unless you have some physics underneath it all, for choosing between these models. The best you can get is, I think this best represents the data because the shape, because of some other argument. That's it. So what we fall back on, and this is the major thing here, is Occam's razor. Occam's razor. Anyone care to paraphrase what Occam's razor is?
Like always choose the simplest solution.
Always choose the simplest solution, yeah. If you have multiple explanations for the same thing, pick the simplest because it's most likely to be right. There's a whole bunch of different ways it's said. Do not multiply causes in excess, I think is closer to the actual quote. But the idea is stick with simple unless there's a reason to go complicated. And that is the exact approach to take with this. If we look at these curves, I'm just going to look at the quadratic and the cubic here for 1 second. Take the linear out. If you look at these two curves, they basically predict the same thing. You know, there's a little bit of difference, but there's not much data there. Up here, the predictions are very, very similar. So unless there is a reason, physics, some master formula that you learned about grade relationships, to pick the more complicated one, which is a quadratic, sorry, which is the cubic's more complicated, you should pick the simple one. You should pick the quadratic. And it even goes back one step. Unless you really, really, really like that quadratic for some reason, the linear is probably the easier one to explain to other people. And so why, you know, this is a little harder to justify. I mean, there's more significant differences between those two predictions. You could actually have a debate about which one captures the structure of the data better. And there's pros and cons both ways. But your default should always be the simplest. Choose the simplest that satisfies the data. Because the more complicated ones will always go closer and have a smaller residual. They have to. That is no evidence whatsoever. That's just a mathematical fact that higher degrees will always have lower residuals. You have to say, why am I allowed to go to that extra degree? Well, because it captures this part that the other one didn't. That's what you need to do as an argument. So in this one, linear and quadratic are pretty much the only two acceptable choices. Because once you get to cubic, there's not much justification for the extra complexity. You get basically the same prediction as the quadratic, and you have to add more complexity, so why would you bother? What's the advantage of going to that extra fit? So that's the kind of argument you get into. And it is hand-wavy. It is completely non-engineering-ish in that respect, but that's the way it works. On that unsatisfying note, let's make one other thing, blah, blah, blah. What I do want to talk about is, now that I've hopefully destroyed any dream that there's going to be a right answer to these things, let's go back and look at the single case. So of the straight lines, so now we're just looking at one choice of the models. How are we getting that one straight line that is the orange line there? Why not some other line that goes in these other directions? This we can actually justify. What does it mean to be the best fit line? Well, in some sense, it means the line closest to the data.